I just want to say a few words. I am Ana Becerril from Michigan State University, and I am the managing director of IRENA. And I just wanted to acknowledge the work of the 2024-2025 organizing committee. The organizing committee is composed of a group of workshops, one from each of the IRENA networks, which includes, of course, our host today, Cameron from Triumph. And they make the program possible. So we really appreciate your work. Thank you. And today is the last seminar of the semester and of the academic year. And thus we need new committee members. So all of the postdocs are invited to volunteer and help put together this exciting program for all of us. Thank you again. And now we can proceed with the seminar.
Okay, well, hello everyone. So today we're going to be hearing a talk from Sivahami Uthayakumaar, and I hope I got that pronunciation right. So Sivi received her MPhil degree in physics from the University of Surrey in the UK, and then she embarked on her PhD program in the University of York, also in Britain, under the supervision of Professor Michael Bentley. Her PhD project focused on looking at the structure of exotic nuclei by exploring the isospin symmetry breaking of nuclei along the n=z line on the proton-rich side of the chart of the nuclides. So since completing her PhD in 2022, she started work as a postdoctoral research associate at the Facility for Rare Isotope Beams, EFRIB, in the US, working within the SUN group, which is led by Professor Artemis Spirou. So in her current position, she's looking at using indirect methods to measure the reactions that take place in stellar environments by studying basic nuclear properties. So, Sivi, whenever you're ready.
Perfect. Thank you so much. Just so you know, can all of you see my screen?
Yes.
I think we can. Perfect. So thank you, Cameron, for the introduction, and also thank you to the committee for inviting me to give a talk at the seminar series, the IRENA seminar series. It's lovely to talk about the work I've been doing so far, particularly focusing on the indirect neutron capture constraints for the astrophysical process. So before I dive in and talk about how we do this, I think we should have a brief overview about the background of the process and different processes leading to the analysis that we are doing. So one of the open questions that we have is how do we produce elements beyond 56 iron? So we know that lighter nuclei on our chart of nuclides, where we have a proton number on the y-axis and the neutron number on the x-axis, we know that nuclei, heavier nuclei up to 56 iron are produced through by fusion reactions. So lighter nuclei from hydrogen-hydrogen fusion and helium fusion all the way up to producing heavier nuclei to produce this allows us to give us 56 iron. Now the question is, how do we produce nuclei beyond this? Because fusion reactions are no longer energetically feasible beyond this rate, beyond this point. So there have been three main processes that help us explain how the heavier nuclei are produced. So the first reaction is the S process, or known as the slow neutron capture process. This process occurs close to along the value of stability. So the value of stability is denoted by the black points here in this chart of nuclides. And typically this occurs around probably 1 to 2 mass units away from the value of stability, with neutron densities probably around less than 10 to the 11 neutrons per centimeters cubed. This process takes on average probably many years in order to produce heavier nuclei, hence why it's called the slow neutron capture process. The second process that is also producing these heavier nuclei is known as the R process, or namely the rapid neutron capture process. And this occurs towards the neutron dip line, so towards the edge of this orange band here in our chart of nuclides. And typically with very high neutron densities of greater than 10 to 20 neutrons per centimeters cubed. So one potential site of where this process can happen is neutron star mergers, and this follows up on the observation of the two neutron star merger measurement that was made a few years ago. The third process is the P process, which is dominated by the photo disintegration reaction. So this process allows us to produce proton-rich nuclei or neutron-deficient nuclei, which is shown by this blue region on this other side of the value of stability. So as of 10 years ago or so, this has been the classical picture for us to understand how heavier nuclei are produced beyond 56 iron. Now, we could try and look at observational data and try and reproduce these abundances, looking at how these processes produce these nuclei. So this is a plot which shows the abundances versus the atomic number of nuclei that are seen in a particular white dwarf star. And this plot comes from Ian Broder and collaborators, where they have looked at the elemental abundances of a white dwarf star denoted by these black points here. What they did was they looked into looking at the R process and the S process using their models in order to reproduce the observational data as shown in this plot. So the R process is shown by the red band in this plot, and the S process is shown by the blue band. So for nucleus, say, maybe around barium to lead, we can see that the S process and the R process reproduce our observational data quite well. However, when we're looking at, say, the lower end of this plot, and we see that the R process and the S process bands do not really adequately reproduce the observational data that we see. So the question is this a combination of the S and the R process, or is this a completely brand new process that will help us reproduce the observational data that we see? And it turns out that if we look at this yellow band, it turns out that the combination of the S and the R process cannot reproduce the observational data that is observed in this white dwarf star. So the combination of the S and the R process does not reproduce this data. So this gives rise to a completely new independent process that reproduces data known as the intermediate or the I process. So where does the I process happen? So I mentioned I process, which stands for the intermediate process, and this happens along in between the S and the R processes. So typically, with typical neutron densities around 10 to the 13 to 16 neutrons per centimeters cubed, and roughly around 2 to 8 mass units away from stability. So we have established that the I process happens in between the S and the R process. Where does this happen, and what are the potential sites? So if we look at certain carbon-enhanced metal core stars, as we have seen in evidence given in the 1990s, Sakurai's object is one example of a post-AGB star that has shown these strange abundance patterns. We can try to explain how we observe this. So if we assume like an S process-like star with a carbon-oxygen core surrounded by a helium and hydrogen layer, what happens is you have your 12 carbon absorbing a proton to produce 13 nitrogen. This 13 nitrogen beta decays into 13 carbon, which then replenishes the production of 13 carbon you have in this environment. The 13 carbon then absorbs an alpha particle around an alpha or helium particle in the helium layer, which produces our neutrons that we need for the I process. So essentially, this is an interplay between the two layers that are the two envelope layers that we have in such environments. So the I process is a result of convective mixing between these two layers. So we established that the I process happens 2 to 8 mass units away from stability. We have an idea of where in a star this happens. But what about the nuclei that are involved in this process? So we know that the nuclei that are involved in the I process pathway, we know the mass of the compound nucleus of the compound nuclei that we're interested in. We know their beta and decay half-lives. We know neutron separation energies. We have these basic information that we have relatively well constrained. The only issue that we have with with the nuclei that are involved along the I process is that we do not have experimental information about the neutron capture reaction rates. So, and this is almost entirely provided by theory. So what this means is we have quite large uncertainties in trying to understand how these nuclei are involved in the I process. So if we look at this plot from Dennis and Koch and collaborators, where you have your atomic number Z versus the mass number, we see as we go away from stability, the uncertainty that you have on your reaction rate increases. So the idea is that we would like to constrain this as well as we can and try and understand how they play a role in the I process. So I have highlighted the 87 krypton N-gamma reaction, since this reaction plays an important role in understanding rubidium abundance patterns and also plays a vital role in the I process. So a little bit more detail as to why we chose to look at the 87 krypton N-gamma reaction is that from the sensitivity studies from Dennis and collaborators and Martinet and collaborators, we have identified that the rubidium abundance distributions is impacted as a result from this reaction. So by studying this reaction and constraining the reaction rate of this particular nucleus, we can try to understand the total strength of the I process in return as a result. There's also been another reaction that has also found to be notable, which is the 88 krypton N-gamma reaction, also determined from Dennis and Koch and collaborators. I will not talk too much about this in this talk. It's currently being finalized by a graduate student in our research group. But however, if you're interested, I'm happy to answer questions on that later. But what we can see is that both these reactions have a significant impact if we look at these correlation coefficients as a result of the reaction index, basically looking at different reactions in a one-zone Monte Carlo method. We see that both of these reactions play a significant role in the rubidium and strontium abundance patterns. So before we dive into how we try to constrain the reaction rate of the 87 krypton N-gamma reaction, we need to actually think about the theory. So as I mentioned, theoretical N-gamma cross-sections have very large uncertainty. And we normally, when we're trying to constrain these reaction rates, we look at a statistical model, which is known as the Hauser-Feshbach model. And the Hauser-Feshbach model states that the neutron capture cross-section, and hence the reaction rate, is proportional to three quantities. One is the nuclear level density, which describes the number of levels as a function of energy, and also the gamma strength function, which tells us the probability to emit any gamma ray with any multipolarity. The third input that we have is the optical model potential. So this describes how our neutron and our target nucleus, so our target nucleus in this case being 87 krypton, are coupled. So these three parameters are essential in order to try and understand how our reaction rate how this reaction, the reaction rate from this particular reaction in question impacts our balances. So the nuclear level density and the gamma strength function significantly dominate the uncertainties in our constrained reaction rates. The optical model potential has large uncertainties when you go further away from stability. So in our case, we would like to constrain the nuclear level density and the gamma strength function. So how do we go on about doing this? So these properties have not been measured for quite a vast number of isotopes. And the reason is because direct measurements at the moment are challenging. What do I mean by that? If we look at these exotic nuclei, they have very short half-lives, which means that creating a target out of radioactive isotopes that decay almost quickly, it's not feasible at the moment. So we need to think of indirect techniques, so as another way to populate the new compound nucleus of interest. So this includes methods like the shape method, the Oslo method, charge exchange, and surrogate reactions. So these are some of the ways that we can try to probe the compound nucleus of interest in order to study these statistical properties. So in this talk, I'll be talking more about the Oslo method and hence the 𝛽-Oslo method, since we have utilized this to constrain our reaction rates for the 87 krypton N-gamma reaction. So before I start talking about the 𝛽-Oslo method, we should probably have an overview about what the Oslo method is. So the traditional Oslo method typically uses transfer reactions or inelastic scattering reactions. So this includes like PP prime reactions, for example. And so we populate a compound nucleus of interest using these techniques, and then we measure an excitation energy and gamma ray energy. So for this, we need a segmented detector in order to measure these quantities. Once we have measured the excitation energy and the gamma ray energy, what we can then do is produce a 2D matrix shown in this figure here, where we have our excitation energy on the y-axis. So these are the states that we populate as a result of this reaction and of the reaction method that we use, and also then use have the detected gamma rays on the x-axis. So in order to get our constrained cross-sections and reaction rates, there are a series of steps involved in the middle. And the first step is that we have to take into account the unfolding of these of the two-dimensional matrix. This takes into account our detector response. And then we extract our primary gamma rays through an iterative process. Now, the primary gamma ray extraction means that from a given state, so for example, if we have state EX here, we extract the first gamma ray that we have emitted from a cascade. So for example, this gamma ray will form a cascade here. So we extract this gamma ray from a particular excitation energy. Now, the primary gamma ray matrix is proportional to our nuclear level densities and the transmission coefficient. So therefore, we can extract our level densities, add a gamma strength function, and normalize them to data that we have for neighboring nuclei, or if we have external normalization factors for this particular nuclei, we can then use that information to then constrain our neutron capture cross-sections. So here's an example shown for the 86 krypton N-gamma 87 krypton reaction, which was done by Ingeberg and collaborators, where they have managed to constrain their neutron capture cross-sections, shown by this red band here. So the 𝛽-Oslo method then takes this traditional Oslo method and combines by this using radioactive ion beams and total absorption spectroscopy. So using radioactive ion beams, we could then use beta decay to populate our nuclei of interest in order to constrain our reaction rates. So how do we go on about doing this for the 87 krypton N-gamma reaction? So as I mentioned, in an ideal world, having an 87 krypton N-gamma reaction would be great. However, we do have we're unable to do this at present. So so in order to populate the states of interest, we used beta decay from 88 bromine in order to populate our states of interest. And so this method is especially quite powerful because this allows us to populate our nucleus using beta decay, but if using low beam intensity, so around 1 to 10 particles per second. And this allows us to access nuclei that are far away from stability. So this method has been made was made by Anne-Cecilie Larsen and Magna Guttormsen in Oslo in collaboration with John Liddick and Artemis Spirod and MSU, hence why it's called the 𝛽-Oslo method. So how did we produce 88 krypton? So this is We did this experiment at Argonne National Laboratory, and we used the Caribou facility. And so this experiment was conducted in 2020 and proposed by Stephanie Lyons. And essentially, in order to produce our beam, we used a 252 californium source, which spontaneously fissions. And so we then use a gas cell to extract the fission products from the source, from the californium source, and use the fission products to be separated in terms of mass. Using the magnets that are provided in the Caribou facility, we are then able to isolate our nuclei in terms of isobars using the MR-TOF located here. So isobars meaning we have extracted the mass 88 chain, being the 88 selenium, the 88 bromine, and the 88 krypton isobar chain here. Once we have isolated these nuclei in terms of the isobars, we are then able to pass them on to our low energy experimental setup, which is shown here. So our experimental setup consists of 3 different detectors. One, which is SUN. SUN is a gamma ray total absorption spectrometer, which detects our gamma rays and allows us to sum up all the gamma rays that we see in our detector to provide the excitation energy. We also have a fiber detector, which detects our beta particles. So, and this fiber detector was developed by Hope College, and where this detector sits, it sits in the middle of SUN in order to use the energies of beta particles for gating purposes. We also have Suntan, which is our tape transport system, which is also placed at the center of SUN. So this allows for our beam of interest. So we have 88 bromine to 88 krypton. We have that implanted in our tape system, which allows us to look at the decay of the 88 bromine to 88 krypton. So a little bit more about SUN. SUN is a very highly efficient gamma ray calorimeter with almost 4 pi coverage. And it consists of 8 segments where we have 3 PMTs for each segment. So we have the benefit of the segmentation of SUN allows us to extract individual gamma ray information, but also allows us to sum all the gamma rays that we have to get the excitation energy. SUN is a very highly efficient detector with an efficiency of greater than 85% for 1 MeV gamma rays, which makes it beneficial for us to do 𝛽-Oslo analysis with. So for an example on how this works, say we put a 60 cobalt source in the center of SUN. We know that 60 cobalt has 2 gamma rays that are emitted, one which is the 1173 keV peak and another which is the 1332 keV peak. And if we look at the segments individually, we can see that these peaks appear quite strongly just by looking at the segments. But if we sum all these 2 gamma rays, we can see a large TAS peak here, which is the state at which these gamma rays come from, so at 2.5 MeV. Using this information, we can then produce our 2D matrix along where we have the excitation energy on the y-axis and the gamma ray energy that we detect on the x-axis. So this is a simple way of explaining how we build our 2D matrix. So going on to the analysis, as I mentioned, we use a 2D matrix in order to extract information such as our level densities and gamma strength function. And this is using the information from the segments from SUN and the total and the sum of the segments in SUN, we're able to devise this 2D matrix for the 88 cryptid compound nucleus. So what we see here is that because we have the isobars from the mass 88 chain, we see that there is contamination from the decay from 88 selenium to 88 bromine. And this is highlighted by the energies in these orange boxes. So since our decay of interest is the 88 bromine to 88 krypton, because this is the compound nucleus interest, we then need to subtract the contributions from the grandmother decay or the decay of 88 selenium. So once doing this and using the fiber detector to help us with the cleaning up of this matrix, we're then able to obtain this finalized matrix for our compound nucleus of interest. So now we can use this matrix and try and get our primary gamma ray matrix and then hence our constrained reaction rate this way. So if we go, this is where the traditional Oslo method comes in. So we have our 2D matrix where we have excitation energy and gamma ray energy on the x-axis. We then do the unfolding procedure, taking into account the detector response and then extracting our primary gamma ray matrix, which is shown in this plot here. And then in order to extract our nuclear level densities, we then need to define a statistical region. So this is the region in which our statistical models will be considered. And also we need to account for the fact that we don't take into account any discrete states in this region. So here I have shown a statistical region of interest that are in this black box here. And then this corresponds to producing this level density shown in the red points in this plot here. So this is our nuclear level density extracted from this work. The yellow band, I'll get onto that in the next couple of slides, but comes from the limits from Mucha and collaborators by using the shape method. So prior to this work, there has been a paper that has been published by Mucha and collaborators looking at the 88 krypton nucleus, where the level density has been produced by looking at both the shape and the 𝛽-Oslo method. So this was done to validate the shape method in terms of its application to exotic nuclear waveform stability. But the only thing that was not done in the published work was determining the absolute gamma strength function. And this is crucial. To constrain our neutron-capture reaction rates. And so therefore, this is where I come in, and we continue trying to get the gamma strength function. So using the Oslo method, this is the gamma strength function that we have extracted. And there is a lot going in this plot, so I will detail what we're seeing here. The purple band that we see is the experimental gamma strength function extracted by Engelberg and collaborators for the 87 krypton compound nucleus, which they have populated through a DP reaction. And the yellow points that we see are previous results looking at photoabsorption data for 85 krypton, which is shown in the green points here, and the yellow points represent the 86 krypton data that was published. Now, in our work, we have deduced an upper band and a lower limit, lower band for our gamma strength function. So the upper band is shown by the blue points here, and the lower band is shown by the pink points. And so essentially having these data that are close by allows us to help with our normalization of our gamma strength function. The dashed black lines are essentially calculations from TALIS, which is a code that we use to try and reproduce our experimental data. And so the black dashed line shows the reproduced data for our upper band, and the solid black line shows the reproduced TALIS calculation for our lower bands. So using our best models for level densities and absolute gamma strength function allows us to extract our constrained reaction rates. So using the combination of our gamma strength function and our level densities, we are then able to extract our constrained reaction rate. So just to point out here, the dashed black line and the on both plots correspond to each other. So this is our upper limit in terms of our constrained reaction rate, and the solid black lines in both plots represent our lower limit of a constrained reaction rate. So if we look at the plot where we have our constrained reaction rates, we have three different parts here. One is the non-smoker calculations that we have shown in the dashed black line, which is a theoretical estimate. And we also have limits from TALIS, where we have default models with default parameters. So this takes into account all the combination of models of level densities and gamma strength functions, and allows us to calculate this maximum uncertainty that we have for a reaction. So this is shown by the blue band here. The orange band represents our constrained reaction rate as a result of our work. And we can see from here that our non-smoker calculations actually fit quite well with the upper band of a constrained reaction rate. So we've extracted our constrained reaction rate. What does this mean in terms of astrophysical importance? So this is a bifurcation plot that was done by our collaborators at University of Victoria. And what we can look at the neutron densities of 10 to the 13 and 10 to the 14 neutrons per centimeters cubed, which is in the range of where the eye process happens. And we can see that if you look at the bifurcation plots of the rubidium versus zirconium abundance ratio, we see that if we do not include this constrained reaction rate for the 87 krypton N gamma reaction, this bifurcation plot shows a large uncertainty. And so you can see this for both neutron densities. But the inclusion of our constrained uncertainty, constrained reaction rate on this bifurcation plots show that our uncertainties have been significantly narrowed. So this shows that this reaction plays an important role in terms of our rubidium abundances. Of course, there is some separation between the two peaks here that we see, and additional reactions can be studied to further reduce our uncertainties in our rubidium and zirconium abundances. So to summarize, we have reproduced our level densities from our published paper from neutron collaborators, and also extracted the absolute gamma strength function to determine our neutron capture reaction rates and also the constrained cross sections. And the improvement of these bifurcation plots done by collaborators at University of Victoria shows that the addition of this reaction, the constrained reaction rate of this particular reaction of 87 krypton N gamma, provides reduced uncertainty in our rubidium and zirconium abundance ratio. There are additional reactions that we can consider to reduce these uncertainties further, which will be detailed in our upcoming publication this year. But the important take-home message to take from this talk is that studying reactions that contribute to the eye process is imperative to understand how these elements are produced and how they play a role in the eye process. So in particular interest, there has been the elemental abundances of barium, lanthanum, and neodymium isotopes are of current interest, and we currently have an approved experiment at Argonne National Lab, which we hope to run hopefully at the end of this year. But also the abundances of yttrium are of interest. So we are currently analyzing the 89 krypton N gamma reaction, which has been pointed out to be an important reaction to understand this. So stay tuned for results about that as well. But just before I end, there are some really exciting times ahead, and there are for indirect measurements, and there is so many things that we can do. So if we look at this plot where we have the projected F-ray beam rates when we get to the 400 MeV per nucleon upgrade, we can see that there is so many different types of nuclear measurements that we can do using these indirect techniques. And we can try to explore how we can measure nuclei that are involved in the eye process in order to understand these abundance patterns, and also with the R process too. So in fact, we have an approved experiment that we're running in June, which looks into how the isotopes around the 128 silver region affect our second R process abundance peak. So this is looking, we'll be using the 𝛽-Oslo method to extract this. But also we can also use these indirect measurements to look at the proton-rich side as well, to try and explore how different astrophysical scenarios such as XRBs, X-ray bursts, also play a role in our abundances too. And we have an approved experiment as well to explore nuclei around the n=z region to explore this further. So before put questions, I would like to thank everyone, all the institutions that are involved in this analysis, and who are in the experiment, and getting me up to speed with all this analysis. And I would like to thank you all for listening.